Hello, welcome to a hopefully quick lesson on how to do least significant bit, LSB first, multiplication in a binary Galois field. So for this example, we're just going to jump right into it. We're going to start with a Galois field of 2 to the 4th. It's just a nice clean example to go with. And let's define our polynomials. So first things first, kind of the most important polynomial we're going to deal with here is our p of x, which is our primitive polynomial. It's the polynomial that defines our Galois field. And for this, we're going to use x to the 4th plus x plus 1. And then we want to think, well, what are we multiplying here? So we're going to multiply a of x, which is equal to x squared plus 1, times b of x, our polynomial b of x, which is equal to x cubed plus x squared plus 1. So, first step we want to do is convert all of these into binary. So, this first one, the primitive polynomial, is going to be a 1 in the x to the 4th place, 0 x to the 3rd, 0 x squared, x to the 1st, and a 1 x to the 0. As you can see, this can also be written as, and the way we kind of get it to this binary is we've got 1x to the 4th plus 0x cubed plus 0x squared plus 1x plus 1. So that is, of course, equal to that. And then we just look for these leading 1s and 0s, and we turn that into a binary number. I hope that makes sense for you. And then we're going to do the same thing to these guys, except we know that for a of x and b of x, they're already within this field 2 to the 4th. So we know that they can't really have this last bit here. They don't have an x to the 4th because they can't exceed x to the 4th. So we're going to say we have a 0x cubed for this one, 1x squared, 0x, 1x to the 0. I'm going to do the same thing here, and we end up with 1, 1, 0, 1. And now the multiplication aspect is actually not terribly complicated. We want to take an iterative approach to this. And if you're familiar with programming, you'll know that we can use kind of I as our iteration variable. And we're just going to start with I equals 0. And what we do is we want to take our b polynomial evaluated at our I value. So b of 0 in this case is, I'll actually switch colors here real quick. B of 0 is a 1. So we're going to say b of 0 equals 1. And then we want to multiply our a into that. So that gives our a of x, of course, is still 0, 1, 0, 1. And then we just want to take that multiplication and accumulate it. We're going to start kind of storing these values up. So then we've also got this accumulate variable here. Accum variable here. And, all we have right now is this 0, 1, 0, 1 times 1, which is going to give us, of course, 0, 1, 0, 1. And then we're done with the first iteration. We're going to go on to the second iteration. I equals 1. And we evaluate b of 1 equals 0. Right there. And here's where kind of the trick comes in. This is what a lot of people seem to get caught up on, is we're not just taking a of x again, we're taking a left shift of a of x. So our next a of x, our new a of x, shifted left 1 is 1, 0, 1, 0. So we take that shift, we're going to multiply it by 0, which gives us, of course, 0. So our accumulate doesn't change. We're not adding anything into it. Or I guess you could say we're adding 0 into it. It kind of depends how you want to look at it. This next iteration is where it gets kind of interesting. We're going to take b of 2, which is 1 again, and then a of x. A of x actually shifts outside of our field. You see, now we have a 1 in that x to the 4th place. We've shifted outside our field. We can't do that. It's a finite field. We're limited. And the way we solve that is just by XORing our shifted a of x by our primitive polynomial. So we're going to XOR this by 1, 0, 0, 1, 1. Of course, 1 XOR with 1 is a 0, 0 XOR with 0 is a 0, 1 XOR with 0 is a 1, 1, and 1. And then we just chop off this last bit because it's a 0, we don't care about it. So that's the a of x that we're now accumulating. Right, so now we have, this is our a of x for this step. We're going to multiply that by 1, and then we want to accumulate that. So our accumulant is now 0, 1, 0, 1, plus, which in a binary Galois field is another XOR operation, 0, 1, 1, 1. 0 XOR with 0 is, of course, a 0. 1 XOR with 1 is a 0. 0 XOR with 1 is a 1. 1 XOR with 1 is a 0. So that's our accumulant at this step. And then we're down to our last iteration of I equals 3. B of 3, if we look up here, is a 1. So we know that we're going to accumulate something. A of x, we take our previous a of x, and we left shift it again. So now we get 1, 1, 1, 0. And then we accumulate, again, our 0, 0, 1, 0. We want to XOR that with our 1, 1, 1, 0, because, of course, you know, this multiplied by 1, we're going to add that in. So we end up with 1, 1, 0, 0. Let me check my kind of answer sheet here. Yep, and that is the answer we should be getting, which, if you just put that back into our polynomial notation here, is going to give you x cubed plus x squared. And that's our answer. That is all there is to it. And actually, if you want to take the time to do this, it's a really helpful exercise, I think, for understanding how this works. But you can actually do the same thing with just decimal multiplication. All you do is you ignore the primitive polynomial because decimal multiplication is in the field of real numbers, which is an infinite field. You're not restricted. So you could do something like, I don't know, 267 times 21. It's a terrible one. 267 would be our A here. 21 would be our B here. And the way this works would just be you take your A times your B index of 0, and then you add into that, through my screen a little bit, you add into that, oh my gosh, you add into that, sorry, your A left shifted by 1, which in the case of decimal is actually a multiplication by 10 rather than a multiplication by 2. You throw your A left shifted by 1 times that 2, and I'm not going to go through the math, but the idea is that it actually still works out the same way. You just don't worry about this XOR step right here where you're worried about bringing something back into the field. So yeah, I hope that helps. Best of luck to you.